Well, hello and welcome to this particular lecture where we are going over the Java features. Let's start with the first one, which is simplicity. We consider Java a very simple programming language, and the reason being that there are various other complex features which are present in other languages, such as C, which has completely been removed in Java. So let's say features like memory management, then pointer arithmetic, pointer operations, then directly you are able to access memory locations using pointers and memory references. Those kind of things just adds complexity to your program. And with Java, these complexities have been removed totally. So which makes Java super simple to program. And also the syntax of Java is very similar to other programming languages. So people or developers who are migrating from other programming languages to Java will have an easier time to kind of learn it. So these are basically why we can say that Java is very simplistic. Now let's see how Java is purely object oriented. So in C, we can directly write a method and execute it. That particular method need not be present within a particular class. But in Java, you cannot directly write a method without encapsulating or probably putting that particular method within a class construct. So at this moment, since we haven't discussed what are class and objects, just consider this in Java. If you want to write a simple method, the simplest of methods, maybe let's say it's just adds two numbers, that particular method has to be present within a class. Any kind of language makes you write the logic within a class, right? We can say that it's a purely object oriented programming language. So in order to understand what are objects and what are classes, we will have a quick look at a particular example. So this is the example which I have for you. Basically, this is the class, and this class name is laptop. So what is a class? Class is anything which represents the blueprint of a real life object. Any object that you see in real life, maybe a book, a pencil, a paper, a TV, a child, a student, anything. That particular object can be represented as a class in Java. Now, let's say we have a particular laptop. So, what makes that laptop a laptop? So, first of all, the brand, there will be a brand for the laptop. Then there will be a graphics processor inside the GPU. Then the CPU will be there, right? Then it will have RAM, it will have a thickness, it will have some portability factors as well. So there are specific properties for a laptop. The real world object that you're considering, we have to model that particular real world object using its properties. So let's say I have a few properties P1, P2 and P3 for a particular object here. So the class is laptop, and the laptop's properties that we are considering are the following. Once these properties are filled with a particular value, right, that becomes an object. From this class, I create a object one. Let's say I have a Apple MacBook Pro. So Apple MacBook Pro is basically a laptop. That's why it is directly being derived from a laptop. These properties will have its own value. So first of all, the brand is Apple, then the graphics processor is M1, then the CPU is M1 Pro, then RAM is 8 gigabytes, and the thickness of the laptop is 15 millimeters. So now you see we are filling values in these placeholder properties. So if the placeholder properties does not have values, then it's basically a blueprint or a class called laptop. But once we populate these properties with certain values, it immediately becomes an object. So from this class, I have created 4 objects, and each of them are for different brands. So class is like a blueprint, objects is something that you are making out of that blueprint by specifying particular property values to that blueprint to make it into an object. So we are done with simple, we are done with purely object oriented. Let's go to distributed. So when we talk about distributed computing, what comes to your mind? So your program that you're writing, it runs over the internet or maybe a network of computers. So let's say you create a small database, in-memory database, and that particular in-memory database has to run on say 5 different machines. That is basically a concept of clustering. I think you should be able to get the picture, or maybe any other server client architecture based software that you can think of, like a chat program, chat messenger program, maybe a in-memory database having multiple nodes on multiple machines. So all this kind of programming basically does few things which are characteristic of such distributed computing. So first of all, it will listen on certain IP ports for messages. Then you will find it very easier to design client server based distributed applications because there are dedicated packages for those applications packaged along with Java. Then also you will have inbuilt out of the box support for processing TCP IP UDP messages as well. And also Java supports distributed methods. Your JVM is running on one machine, it can remotely invoke another method on another machine. So this is typically another JVM. So let's say this is JVM2 and this is JVM1. So from JVM1, process can invoke a method on a particular class or an object which is running in JVM2, and this is possible using something called RMI. So that is also supported. So all these things adds to the distributed features of Java. Now let's move on to robust. Why do we call Java robust? So in case of an error, normally what we have seen in C++ days, that when an error used to occur, we used to lose data, the program used to hang or maybe crash abruptly, we will get some log messages. The intended output of the program was not achieved in most of the cases. So we need something called exception handling, and this exception handling features is very well baked into Java. And also Java supports robust memory management, due to which automatic sufficient memory allocation is also done by the JVM for a program. So you have to worry about your business logic and let the JVM worry about allocating and deallocating memory in the backend. Then we have something called compile time checks and dynamic checks, which are also implemented, which makes Java a robust language to program in. Now coming to security aspects of Java features. Now let me tell you, security can be a separate topic in itself because it is very vast. The scope of that particular topic is outside of this particular lecture. But for now, it's sufficient to say that Java has inherent mechanisms in JVMs that make it extremely safe and secure to develop for the World Wide Web. Then coming to the next buzzword, that is the architectural neutrality. We have already talked about this in length in one of our previous lectures, but just to jog our memories, JVM implementations are machine and operating system specific, but our class files or the bytecode files are machine independent, which can be run by these machine specific JVMs. This is what makes Java achieve architecture neutrality. Now coming to portability. Due to architecture neutrality, we can write the code once and then run the compiled runnable jar or the class file on any machine, provided it has the corresponding JRE available. That is the only requirement. Whatever machine you are running on, just get the JRE and make it available on the class path, set it up properly. Then take any class file that you have written, maybe on a Windows machine or on a Linux machine, bring that over and run it on that particular system. So that's a very, very big advantage. So let us discuss how Java achieves high performance. So this is a debatable aspect. Some of you might say that no, Java is not that performant, C or C++ is much, much better. But there are two sides of every coin. So Java achieves high performance using certain optimizations at the JVM level. Initially, Java code is compiled to class file or bytecode, which is then executed by the JRE using an interpreter, which is a bit slow than traditional interpreters seen in other languages. For this, we have just-in-time compilation within JVM, which improves the performance by detecting possible regions in code which can be cached for future executions. And this is just one of the many optimizations it offers. So in tandem, both interpreter and JIT compilation speeds up our code execution within the JVM, ultimately helping us achieve higher performance. Then coming to multi-threaded. So basically when you launch your program, a single thread is going to run your entire code. That is not possible for all the scenarios. Whatever you are coding might not be sufficient to have just a single thread. So if a single process will not suffice your workflow, you are free to use multi-process or multi-threaded workflows in code. For example, you can create a server which will spawn a separate thread to service each incoming request. This can be easily achieved in Java. We consider dynamic properties of Java as well. Why Java is dynamic. So this concept further dealt with in our upcoming lectures when we dive into class loading, how classes are loaded into memory. But just for now, it will suffice to say that classes are loaded onto JVM on a need basis. For example, when a programming is executing and there is a need for a functionality which a certain class offers, which is not yet loaded into memory, the class loader will load that dynamically during runtime. This efficient use of memory optimizes the runtime or execution speed of a program. So let's say there is a heavyweight class which offers hundreds of functionalities. We don't have to load all the classes at one go. So the program startup is much faster. As and when those functionalities need, we will load the classes which is related to them. So this is just one tiny aspect of the dynamism of Java. There are multiple things that can be discussed here as well, but just in the interest of time, I thought of providing you just one simple example. Those are the features of Java. Hope you enjoyed them. And with that, we come to the end of this lecture. Thank you.